You want to just talk about sampling distributions in general?
Can we go over question 2 on 8.1?
Sure. Actually, I have your 8.1 pulled up right here. And I think I see what part of the issue is. So let me grab that problem or parts of that problem. So there are a couple of interesting things kind of sort of hidden in this problem that it makes it a really good problem for us to talk about. So let X, that's our random variable, it's supposed to represent the height of certain species of trees. Assume that it's has a normal probability distribution with an average of, or a mean average of 26.5 feet and a standard deviation of 97.6 feet. Now, automatically, that should seem a little bit odd because 26 feet is, not that it's short, but 26 feet, got a 26-foot tree. It's a really bad tree, but that's okay. That's 26 feet. And this almost 100 feet as a standard deviation, that standard deviation is very large in comparison to that 26, right? So if we tried to go, 3 standard deviations above and below, very quickly we're going to get into negative height on trees. Is that fair? And we shouldn't have negative height trees. But this standard deviation doesn't seem too unreasonable because the variance in height of trees is really very dramatic. You have trees that are several hundred feet high out there. So I actually don't believe them when this problem says that this population is normally distributed. It's actually almost impossible for it to be normally distributed, given the data they've given us. Because that would mean we'd have a bunch of negative height trees. If we looked at the distribution of tree height, you would tend to see a lot of trees that are shorter and then small amounts of the super, super, super tall redwoods and sequoias and stuff. It would have a mean that's skewed towards that, 26.5. It would have a median, I think for trees it's somewhere around 18 or 19 feet, I don't remember. But this huge standard deviation of about 100 because of all these super, super, super tall trees. Does that seem reasonable as what tree distribution should look like? So they said, assume it's normal. I don't know why they said that. They shouldn't have, because their data says it can't be normal, and they're trees. Trees shouldn't be normal anyway. It is of a particular species, but that's okay. But to use a lot of the tools that you've been using, we need to have a normal distribution. And the picture that goes along with this problem draws a normal distribution. It gives you a drawing that's a nice normal distribution to label. So what's going on here? Well, the idea is, the issue in this problem and in this section is that we are not looking, we are not looking at this population distribution. This is not what we're considering. Not the question. We're told about this problem. We are told what its mean is. We're told what its standard deviation is, 97.6. What we're asked is about the sampling distribution. So I want to make sure it's really clear the idea of what is a sampling distribution. So I brought a tool here today. So let's say we build this distribution a lot like the tree distribution. So there's a lot of small trees out there and very, very few big giant trees. So that's our population distribution. That's what the trees look like. We're supposed to go out and take a sample. Now their sample here is of 123 trees. The highest this thing goes is 25 at a time. So we're going to go with 25 at a time. So you intend to measure a random sample of 132, again, we're going to use 25, of 132 trees, and look at how those are distributed. So I'm going to do that. I'm going to take a sample of 25 trees. Now, just like our population, it's not done yet. Okay. Just like our population, this distribution, it's referred to as our sample distribution. That sample distribution kind of looks like our population does. Most of them are fairly small trees. We did get one big tree out here. But it kind of mimics what our population looks like. If our sample size was larger, it would fill in a bit more. But that looks kind of like our population does. And grabbed an average, a single average. What's the single average there? I can't quite see it. Of 8. Okay. Grabbed that. Well, these values are not the same as our trees, but grabbed a single value for our mean and dropped it there. Fair so far? Well, what if we take another sample of 25? Okay, we got to wait for it to sample 25, but it should, the sample distribution, often it's referred to as a data distribution, just because it's easier. Our population distribution is highly skewed right. So our data distribution is somewhat skewed right. This one, not quite as much. But again, our mean, notice our mean landed in about the same place. Now we could do this over and over and over again, and that's kind of what they're asking us to do. But I don't want to watch all of them fall. So this will let me do 5 at once. So if I hit this 5, it'll do this sample from our population. Slowly. It'll do this sample from our population and grab us a mean, but it'll do it 5 times in a row without us having to watch it. Fair? So do it 5 times in a row. Now, notice, this is the super, super important part here. Notice our population is highly skewed. Our samples come out skewed. But look what's happening to our distribution of means. This is what the sampling distribution is. It's this third one that's in blue. It is a distribution of averages. Fair? So when we're asked to look at our sampling distribution, we're looking at a distribution of sample values. Now I'm going to do this a whole bunch more times, 10,000 times. What does this curve start to look like? Notice it doesn't look like our population curve. It doesn't look like our data distributions. It should be looking like a nice normally distributed curve. Because our sampling distributions, because they're measuring their distributions of our averages, those averages are held fairly tight around the actual average of our data. Notice the average of our data is up here at 8. The average of our sampling distribution so far is 7.98. The average of our data and the average of our sampling distribution are roughly the same. And that's exactly what should happen. This is a distribution of those averages. The distribution of averages should land around the average. And while the data distributions match the skew of the population, the sampling distribution is a nice, fairly tight normal curve. If we jump over here and do this 100,000 times, or 200,000 times, or 300,000 times, if I want to keep hitting it, we keep this nice, tight distribution around our data, around our mean. So we're not, in this problem, we're not looking at this curve of our Here, the variable is tree height. This isn't the curve we're looking at in this problem. We're imagining somebody took sample size 132, samples of 132 trees and came up with averages and distributed all of those averages. Well, all of those averages should land in a nice, tight, normally distributed curve. Now, the average, the mean of that normally distributed curve should match the same 26.5. The average of the sampling distribution, the mu of the sampling distribution, should equal the mu, the mean of the population. And that's always nice. The average of one should match the average of the other. But the standard deviation shouldn't match. This standard deviation is fairly wide because it's measuring all these different trees, the little trees and the big trees and all the trees. But this is a distribution of averages. All of our averages should fall pretty tightly together. So the standard deviation down here, the standard deviation of our sampling distribution, is not equal to the 96, is not equal to the standard deviation of the population. It's much smaller. How much smaller? Depends on what size your sample is. The bigger the sample, the more it's going to take that 97.6 and shrink it. By how much? By the square root of that sample size. So to generalize, why is my eraser not working today? To generalize, to find the standard deviation of the sampling distribution, we take the standard deviation of the population, which should, it's going to drive me nuts today. Take the standard deviation of the population and divide it by the square root of that sample size. Why the square root of the sample size? You might remember standard deviation was a big square root. So we're essentially dividing that into that square root. So we need that square root on it. So the problem that you were working on, Tessa, you put the 26.5 there for the mean, which is true. The means should match. But the standard deviation for this sampling distribution And the symbol I'm using I was using SD over here for standard or for sampling distribution, but should really get in the habit of using the X bar, because this is specifically a sampling distribution of means. So the sigma standard deviation of a distribution of means should end up being that 97.6 divided by the square root of the 132. And that's going to give us the standard deviation of our sampling distribution, as opposed to the standard deviation of our population. Now, I can load up my calculator and find that, but loading up this calculator takes a minute. If you guys have calculators out there and can bust out that value, that would be handy. If not, I'll have it here in a minute.
Yeah, I got 8.494 as well.
So 8.49. Nice. Again, much tighter because of that, because it's an average of 132 trees. So it pulls that variance way, way, way down. And that distribution then will go from the 26.5. The first standard deviation will be that 26.5 plus the 8.49. So what is that? About 35-ish. And down 8.49, which is going to be, what, about 18-ish? And give us a nice, tight sampling distribution. So, Tessa, how do you feel about that?
Good, but I just did the question, and it still says that, like on the graph, when I added the 8.49 to the mean, it still says it's wrong. Because I got 34.99. And I just put in the 2 decimal places because it says correct 2 decimal places.
Yeah. See, Bell River distribution simple means the scale and horizontal axis, standard errors, average distribution, decimal places. That's weird. Let me check. I mean, I wouldn't disagree with both of you, but about 97.6 divided by the square root of the 132 is 8.49. Yeah. And if we add the 26.5, 34.99. So what you're saying, why do they say that answer is 43? Doesn't make any sense.
And then also the...
Oh, that's why. That's why. So do you want to know why?
Yes.
There's a tick mark there and a tick mark there. And the box that it wants is this one and that one. So this is the 34 point whatever. Add another one, and that's the 43.48 that it wants. Does that make sense? Its box is for 2 standard deviations out. What was that, Tessa?
Yeah,
What was that?
That makes sense. I didn't see that it was 2 away. I thought
Yeah.
it was 1.
I didn't either when I saw it first. But yeah, that's why.
Okay, that makes sense.
Cool. Now, there are a couple of restrictions to this. For this to work, as I said, we've got some population, and for sampling distributions, this population was skewed. For the sampling distributions, this population can really be anything, any weird, horrifying shape, because data is sometimes messy. So if we've got messy data, somebody's going to come around and take samples. And if we took a whole bunch of samples, like if I had everybody in class go out and take a bunch of samples, each of their samples should roughly mimic the population distribution, because that's what a sample is supposed to do. An individual sample should mimic our population. So they'd all look roughly the same. Some of them would be a little different because, that's what happens when you gather data. Some of it's a little more varied. So if we looked at everybody's data distribution, they'd all look roughly the same, and each person would come with their own mean. They'd each have their own different mean, depending on exactly what their sample was. Now, the restriction here, a couple of restrictions. One, all those sample sizes have to be the same. So for a data distribution like this, all of our samples have to be considered to be the same size. So when I sent everybody out to find data on trees or whatever we're finding data on, all of them had to go get samples the same size. But everybody would come back with a slightly different mean. But you'd probably expect, and you'd be right, expect these means to all be relatively close together. Some of them might be a little bit more one way or the other, but all those means should probably be relatively close to each other. So if we collected all of those means into one big pile of means and analyzed it, all of those means would fall in a fairly nice, tight, bell-shaped curve. And that's what we were seeing happen. There it is, over here. Even with really weird data, and I could make this data all kinds of crazy. If we took a sample, that sample would, let me clear those. That sample should mimic our population. And, it is. It's dutifully looking a lot like our population did. But we'd find a mean fairly close to the mean of our actual data. And if we did this over and over and over again, we would get a fairly nicely normal distributed set of data. Fair? If. There are two ifs here. One, if the sample size is large enough. Here I'm doing a sample size of 25. That's fairly small. If we took that sample size, let's go all the way down to 2. Let's say we took a sample size of only 2. So I told these people, go find 2 trees and bring back the data. Well, if you're only finding 2 trees, the chances of finding really big trees and really skewed data goes way, way up. So look at that sampling distribution now. Is that nice and normal? It's all over the place. So for our data to be nice and normally distributed, we have to have that sample size, N, be large enough to force it to be normal. Now, 25 seemed to work okay, but the general threshold is 30. So to guarantee that our sampling distribution, our distribution of means, is going to be nice and normal, we generally want to use at least 30. Again, this tool only goes up to 25 for its own reasons. But at 25, no matter what I do up here to make an ugly distribution, no matter how crazy those data distributions look, trying to model this population data, if we collect all the means from it, it should end up looking fairly normal, with its own average in the same place as the average of our data, and a fairly tight standard deviation. So that's restriction 1. This is going to work if our sample size is at least 30. So this 132, plenty, way more than enough to guarantee normal distribution. So that average for our population of sampling distribution, or population of, sampling distributions, well, a population of data distributions, technically, the mean for our sampling distribution will be essentially an average of averages. It will equal the mean of our data and have a fairly tight standard deviation equal to the standard deviation of the population divided by the square root of that sample size. If our n is larger than 30, no matter what our original population looks like. Now, what if a sample size of 30 is hard to get? Well, what if we just don't have a sample size of 30? This still can work with smaller sample sizes, but with a smaller sample size, it's required for our population to be normal. If you want to go with a small sample size, your population has to be normal, which is likely why this question said, assume it's normally distributed, because then this automatically works. Then even if this n is small, and it's probably a variable in this problem, the computer will shoot out a different number there. So even if this number is small, it works. So if your population is normally distributed, then all of your little data distributions, everybody's individual little data that they collect, should be roughly normal. That one's a little tight. Roughly normal. Some of them will be a little skewed just because, again, you're collecting data and you get, variance. But no matter what the sample size is, for n equals anything, your sampling distribution will be guaranteed to be normal when we collect all those averages. Again, the average of our average, the average of the sampling distribution, is going to equal the average of our population. It's going to equal that original average. And again, it's going to have a standard deviation that is significantly tighter than our original data was. It's going to be our original data's standard deviation divided by that, again, square root of the sample size, no matter what the sample size is. And again, we can see that happening if we model it here. Oops, no, I'm fine with that. If we have data that's fairly normally distributed, and that's, roughly normal, And again, we collected data. Let's make it even a small sample size of 10. If we collected data, that data should look somewhat normal, more in the middle, less on the outside. Should be, again, more in the middle, less on the outside. But, you know, it's a little bit not great. It's only a sample size of 10. It can't get that nice, perfect normal to it. But if we did this a bunch of times, went out and collected 100,000 samples, each sample a sample size 10. Keep that in mind. This is not a sample size of 100,000. This is 100,000 samples of sample size 10, and collected all their averages. Notice not only is it normally distributed, it had to be since our original population was normally distributed, but notice it's much tighter than this one is. These scales are the same. So this is a much tighter distribution than this one is. If we increase the sample size to 25 and do it again, notice it's even tighter. Compare that one to that one. Even if we go to n equals 16, kind of in between, it's a little bit wider than the 25, a little bit skinnier than the 5. Even at n equals 2, it'll come out normal and a little bit tighter, but not much, because it's only sample size 2, but it's still normal because our original population was normal. Now again, this applet, that's what this thing is called, this little applet is taking those samples, finding the mean of the samples from this data, and laying it down as this is our average, our mean of the sample. It's doing it over and over again. This would be doing it 5 times. Now it's 10 times. And the more it does it, the more that's going to start looking like a normal curve. I'm doing it 5 samples at a time. Now this would take forever. But if we look at the full sampling distribution, the full sampling distribution is every possible sample of size 25. We get a very nice, normal distributed curve. Fair? So the other qualification, if your sample size is small, you can still use the sampling distribution with this standard deviation divided by the square root of the sample size as its standard deviation, as long as your original population was normal. If your original population wasn't normal, if your original population was ugly or skewed or weird in whatever way, that's okay. You can still use this nice sampling distribution as long as our sample size is above 30 for means. Questions about that so far? Now, there's some language we got to play with here. It's inconvenient to talk about the standard deviation of the population versus the standard deviation of the sampling distribution. And the reason that's inconvenient is, well, it's a mouthful. And when we want to be able to say standard deviation and know which one of those we're talking about. For the means, it's not that important. If we look like, oh, are you talking about the mean of the population, which we generally just call mu? Or are you talking about the mean of the sampling distribution for means? Well, we don't really worry about which one of those we're talking about because they're the same thing. They're equal to each other. Fair? So if somebody says, the mean is 48, well, do you mean the mean of the population or the mean of the sampling distribution? Yes, because it doesn't matter because they're the same value. But the standard deviation of the sampling distribution of means isn't equal to the standard deviation of the population, sigma. It's equal to the standard deviation of the population divided by the square root of the sample size. So they're different. When we write it out in notation, we can see that sigma x bar. So visually, when we write it, that x bar tells us it's a distribution of means. So, okay, I know that's a standard error for a sampling distribution of means. But in speaking, we don't want to have to say the standard deviation of a sampling distribution every time we want to say standard deviation. So what has happened over the years is this particular type of standard deviation, the standard deviation of a sampling distribution, has built up a special name. Instead of being called the standard deviation of the sampling distribution, it's referred to as standard error. It's still describing an amount of variance. Remember, deviation was how much our points or how much our data deviated from the mean. This standard deviation for the sampling distribution is doing the same thing. How far off from the true mean were these sample means? How much error was there in the sampling? So it's describing the same thing, but calling it standard error focuses your audience on the fact that it's for the sampling distribution. If we go back up to Tessa's problem up here, which is absolutely covered with writing and stuff, if we go back up to this problem that we were looking at today, we're specifically asked the scale of the horizontal axis is the standard error of the sampling distribution. Standard error automatically means we're sampling distribution. So the fact that that said standard error means we should be in the sampling distribution and we should be using that sigma divided by or standard deviation divided by the square root of that sample size. It automatically tells us to take that standard deviation and shrink it based on that sample size. Fair? So when you see that word standard error, that's what it's referring to. Now, this is specifically the formula for standard error of a distribution of means. In 8.2, we talk about the distribution of proportions instead. We go back to binomial distributions. That doesn't have a sample standard. Well, it does have a data standard deviation, but we don't use it. It has a different way of finding, or a different formula we're going to use for standard error. So you do want to separate, this is the standard error for a distribution of means versus the standard error for a distribution of proportions that we'll work with in 8.2 tomorrow. The formula will be slightly different, but it will mean the same thing. And frankly, it looks the same. It's still a nice normal distribution. So you want to start working on that language. We don't call the standard deviation of a sampling distribution standard deviation anymore. We call it standard error, and really just to make the language a little bit more useful. Does cause a little bit of a hiccup in trying to kind of learn all of this because it's, a new vocabulary word. But once you're used to using it, it's actually very handy to have the language be distinct. Does that seem reasonable? So at that point, we could even ask for a population, population with a mu. Again, mu, because it's a population, average population, we use the Greek because it's a proportion. It's a value based on the population, so it's a parameter. So we use the Greek mu. So population with a mu of 32 and a standard deviation of, I don't know, 17 for a sample size of n equals 100. Find the standard error. Now, it would be common to say find the standard error of the sampling distribution, but it wouldn't be necessary to say of the sampling distribution. Standard error means you're in the sampling distribution. But for politeness, they will often say find the standard error of the sampling distribution. But what is standard error? It's the standard deviation of the sampling distribution. How do we find it? Well, it's our standard error of our sampling distribution. Oftentimes you'll see people write SE, by the way, for standard error. It's the same thing. So either one of those is fine for standard error. I'm going to use the sigma x bar. Try to use that more because that's what your book likes to use, but your book will use SE every once in a while. But how do we find it for a distribution of means? Take the original standard deviation for the population divided by the square root of our sample size. So 17 divided by the square root of 100, 17 divided by 10, 1.7. And that could literally be the entire question. So I've been talking for a while, way too long, frankly. Andrea, Tessa, Kim, you got any questions based on that? Any thoughts on that?
So, did you record yesterday?
No.
But you had a class.
No.
Okay, so are you just starting 8-1 now?
Yes.
Okay, and what time did it start at?
10:20.
Oh, okay. My time's all kind of screwed up because I had planned on that other class. That's why I was late. Are you going to record this one?
I am recording this one, yes.
Yeah. So I can go back and listen to the first part?
Absolutely.
Oh, great.
Excuse me. Now, we will use sampling distributions for a fair amount of important things. It's kind of surprising. Like, it kind of seems like it requires us to know a lot more about the population than we normally will. But it's actually surprising the number of tools that we will build out of our sampling distribution. But it does have some good uses, some really important uses all by itself. And this question is a fairly good example of that. So the lengths of pregnancies in this small rural village. So somebody's been collecting data on the lengths of pregnancies in this village for a long time. And we know the population mean for that number of days of the length of a pregnancy should be about 261 with a standard deviation of 16 years. So we're told an average and we're told a population standard deviation. So we're used to questions like this from chapter 7. In what range would you expect the middle 98% of pregnancies to be? So where's that middle 98%? We can do that problem, right? That's 261. It's got a standard deviation of 16. If we want the middle 98%, that means there's 1% down here. So 0.01 down there. And then that's a calculator operation from there, right? Where's my calculator? Oh, there it is. We have a proportion and want a value, so that's an inverse. So inverse normal. And the inverse normal wants, see the area, 0.01 for 1%. Our population mean is 261, and our standard deviation is 16. Now this is asking about individual pregnancies, so it's the standard deviation within our population. So it is just the 16. So that's 223 down there. And if we wanted the upper one, there would be, I guess I could figure out how far away that is and do the math, but I could also just say at 99%, that boundary is 298. So 298. So the middle 98%, so almost all of these pregnancies will fall between 223 days and 298 days. So that's the middle 98% of pregnancies. That's essentially a chapter 7 question. But if instead of looking at individual pregnancies, we look at sample size 42 of pregnancies, so let's say, I don't know, a particular clinic handles about 42 pregnancies a year. So for them, they would have their own average. So if you're sampling the average from that particular place or that particular clinic or clinics of that particular size, their average should still be the 261 because they're drawing from the same population. But their average, while it's still going to be 261, their value for the average of every 42 pregnancies that they look at is going to be much tighter, much more tightly distributed than the individual pregnancies. This average of every 42 pregnancies should be tighter than each individual pregnancy. Now, it's important that that idea of why is that tighter makes sense. If you're looking at individual pregnancies, having really short or really long pregnancies, the odds of that happening for are fairly high. Some individuals going to come in really premature or really late. That's going to happen a fair amount of the time. Not a lot, but you're going to get 1% of the people that come in less than 223 days. When you average 42 people together, yeah, you're going to get some of those really short and really long values, but when they go into the average, they're going to be averaged out. They're going to be mitigated by the other 41 data points that you're looking at. Fair? So to get an average of 42 people, where that average is still down in this range, there's not a 1% chance you're going to get 42 people that come out in that range. The odds of having all 42 down in that range is very, very, very tiny. So we're not going to see averages down in the 223. Our averages, remember, this is a distribution of averages. So this 261 is the average of those averages. We're going to see averages that are much, much tighter. How much tighter? Well, how much tighter? We're going to divide it by the square root of that sample size. That's how much tighter. So what's 16 divided by the square root of 42? I don't know, whatever 16 divided by the square root of 42 is. I'm going to go with 2.47. 2.47. That much tighter. 2.47. So individual pregnancies have a standard deviation of 16 days. Averages of sample size 42 have a standard deviation of 2.4, or more technically, a standard error of 2.47. Remember, this is standard error at this point. So when we want to find where the middle 98% for that is, that bottom 1% of sample sizes 42 isn't going to be 232 anymore. It's going to be much, much further in. And the 298, we're never going to get averages way out there. That top 1%, it's going to be, again, much, much, much tighter. Again, how much tighter? Well, let's do the math, find out how much tighter. I'm going to bring up that same inverse norm. So inverse norm still 1%, that lower boundary. Still has a mean of 261. The mean of the sampling distribution is equal to the mean of the population. But our standard deviation is no longer going to be our 16. It's going to be our standard error of 2.47. Making this all the way up at 255. And we could do the other one with the 99%. Again, still with a mean of our sampling distribution of 261, the mean of the sampling distribution, same as the mean of the population, but with our much smaller standard error, gives us a 266 there. Again, much tighter. So how would these sound different if we were saying it? If we consider 98%, I'm going to kind of just grossly call 98% almost all. I think 99.7 is what we were calling almost all before, but so I don't want to use that phrase if we already used that phrase. I'm just going to say, yeah, most, all. I don't know. It's hard to come up with a word there. I am going to use almost all. Yeah. So almost all, 98% of pregnancies fall between 223 and 298 days. As opposed to almost all, 98%, of it's hard to word, of 42 pregnancy averages fall between 255 and 266 days. Now, why might we care about this? I mean, don't you want to know for individual pregnancies? Well, again, say you're a clinic and your clinic does 42, usually 42 pregnancies that they handle a year. If you're going to make sure you have enough supplies for that, and you want to make sure that you have like well enough supplies for that, or why that should be days. I'm not sure I like this particular metaphor for this problem, but we're going to go with it. If you had to take care of an individual person, you might want to prepare for that 298 days. But if you were caring for 42 people a year, if you wanted to get enough supplies to make sure you handled an extreme year, you wouldn't want to plan on those 298 days. You'd plan on the 266 days. That way you would end up with enough supplies for the highest thing you would expect to see out of your average of 42 without having to oversupply based on the individual value. Now, again, pregnancy days, I'm not sure. Ooh, let's do this. Let's do it that way. I like that. I like that. Okay. So if, sorry, I'm really happy about that. Figured out a way to make this make sense. Vitamins. If you had an individual pregnancy and you wanted to make sure you were not going to run out of prenatal vitamins, not prenatal because you're natal. Anyway, you didn't want to run out of your vitamins through the entire length of your pregnancy. You'd want to get 298 days worth of those vitamins. Because that's going to be, 99% chance you're going to have, that's the 99% chance, 99% of the furthest length of a pregnancy is going to be 298. So that's your threshold for buying enough vitamins. But if you're going to be, again, an organization that's providing vitamins, you're not going to get enough to give every pregnancy 298 days of vitamins. You're not going to need that many because the chances of all of your 42 people falling up in that range is minuscule. So how many should you get as the clinic helping provide vitamins for these 42 pregnancies? You should get enough for 266 days for each person. That way, even if you do have some of these extremes, they're going to average out with some of the lower values. And that 266 is the highest, 98%, the highest you would expect your 42 person average to end up being. I need to use a better example than pregnancy for this, but that's what came up on Tessa's homework. So I'm going to blame her. But we'll see more examples of this, that if you're dealing with larger scale, concerns other than individual concerns, using these sampling distribution values is much more accurate and much more efficient than dealing with how are the individuals organized or how are the individuals spread out. Is that fair? That example got a little bit convoluted. Sorry for that. Before we go, Tessa, you asked a problem. Andrea, Kim, do you have anything you want to look at other than this problem that Tessa wants to look at?
Not yet. I'm a little behind. But I'll get caught up.
Okay. Andrea, how about you? How are you doing with all this stuff?
I think I'm the same as Kim. Just trying to soak it all in, I guess.
That's fair. So this problem number 7 from Tessa for Tessa. A problem's value is normally distributed. Okay, normally distributed population means it doesn't matter what the sample size is. We know we're going to have a normally distributed sampling distribution. So population has values normally distributed. With that mean that standard deviation. You intend to draw a random sample size of 135. The 135 is so big, much bigger than 30. So even if it wasn't normally distributed, we'd still get to use this. So find the probability that a randomly selected value is less than 200. So it's asking about a specific value, right? Where do values live? Do values live in our population, or do values live in our sample of size of 135? They're not asking about a sample size of 135 yielding an average of 200. They're asking for an individual value from the population. Is that fair?
Mm-hmm.
So if they're asking for an individual value from the population, then our mean is 199.7 and our standard deviation is 13.3. So what is the probability that a value will be less than that 200.2? Whatever that area is, right? And that's a normal distribution. So we could grab our normal distribution tool, second distribution, norm dis CDF, lower, very low, upper 200.2, 200.2, mu of 199.7 with a standard deviation of 13.3. Now, does it make sense, Tessa, why I'm using the standard deviation of 13.3 as opposed to finding standard error? Yes, good. Everybody else make sense why we're still using the 13.3?
Yeah.
Okay. So that's 51%. Now that 51% should be hopefully fairly reasonable, because this 202 isn't that much above the 199, right?
Yeah.
So it's just barely above that 199. I mean, my picture was out at the 13. I was like, well, it's not that far out. It's just barely above that. Fair? Particularly compared to this big standard deviation. I mean, this is a little amount of change. in comparison to that 13. Fair?
Yes.
Then the second part, find the probability that a sample size of 135 is randomly selected with a mean of 200.2. So again, we're not finding a value at 200.2. We've taken a sample size of 135 and found that that sample size is less than that value. So it's a much tighter distribution. The mean is still 135, but our standard deviation is going to be a much smaller standard error. Again, how do we find that standard error? Well, we take the standard deviation of the population and divide by the square root of the sample size. So we divide by the square root of 135. That should be somewhere around 1, I think. So that's 13 point, I forgot, 3 divided by the square root of 135 is 1.14. So is 1.1, oops, 1.14. Is that right? 1.14? Oh, I closed it. I'm going to assume that's right.
Yep.
So 1.14, so much, much, much smaller. So instead of having the one standard deviation cut at 13 and having that 200 or 200.2 be way far in, our standard deviation is now only 1.14. So the fact that this is off by, okay, it's still quite a bit less than 1, but it's much more into that distribution. Why do I have 135 there? Sorry, it's 199.7. It's much more in there, so I would expect it to be, this was just 51. This is going to be 50 and a good chunk more, I would expect. Tessa, does that expectation make sense? Why I expect it to be, you know, yeah, 50% like the other one was, plus a much bigger chunk? Good. So, whoop, gotta bring that calculator back. You guys have calculators. You guys can do it. I know you can, but sometimes it's helpful to see it. If I can't get it out from under my, that doesn't matter. So, same distribution. So again, sometimes it's weird because it's like it's the same question, almost, except our standard deviation is now our standard error. And that's the whole point of a lot of these questions. They'll ask you the same question twice, but one question will be in the population distribution or in a data distribution. The other question will be in the sampling distribution. The only thing that changes is that standard error, but it makes a big difference. 60, more or less 67. So that chunk was really big, 67%. Tessa, does that help? Cool. Okay, so go play with those. See if this adds some perspective to those. Hopefully it does. And I'll see you guys tomorrow with good questions. You guys were good today, but you were kind of quiet today. That usually tells me that we got to get caught up. So come back tomorrow with some good questions, okay?
Thanks.
All right, thank you.
Very welcome.